to be a review of the concept of enthalpy, specifically using experimental data to calculate the delta H naught of a reaction. So we haven't used this term yet, but we've already done one estimate of the delta H of a reaction, which is a couple of videos ago we talked about using bond energies to estimate what at the time we were calling the change of energy. And now we're being more specific and more careful about our framing of that. And we're thinking of it in terms of the change in enthalpy. And we're going to do a calculation today to show how we calculate change in enthalpy for a chemical reaction using experimental conditions. We're going to see that a lot of the experimental data has been carefully calculated and tabulated, and in the next couple of days we'll see how we can use tabulated delta H values to calculate the delta H of any reaction. But today we're going to focus on experimental conditions, but we're going to start with what do we mean by this business enthalpy, right? So what does this word enthalpy mean? And there are more precise definitions which you will learn if you are a chemistry major in physical chemistry. But for now, and if you've had that class, I'm going to not be as careful as that. So this is how I think of it. I think of it as chemical potential energy. So it is a potential energy that is chemical in nature. What do we mean by that? It's just like any other potential energy. So the energy that a rock has that's sitting on top of a mountain. If you give the rock a little nudge, it'll roll down the mountain because the potential energy it has from its position will be changed into kinetic energy. In the same way, this is chemical potential energy in that you can't see it. It lies within the relative positions of the electrons within the orbitals in their various compounds between reactants and products. But where we see it expressed, so just like the boulder rolling down the hill, if its potential energy is being converted into a visible form of energy, in other words, kinetic, in the same way that this chemical potential energy that is enthalpy is expressed or observed as heat. So it's observed in a chemical reaction as heat. All right? And that can be, and remember from our previous discussion, heat can be absorbed or released. All right? So we don't mean necessarily that things are getting hot. They can be getting cold as well. Either way, there is a transfer of thermal energy, which is what we call heat in chemistry, and that heat is going to be kind of the telltale sign that there's a change of enthalpy occurring. For reasons that you don't need to worry about, enthalpy is abbreviated with the symbol H. All right, so H is capital H is the abbreviation for enthalpy, and so and then a lot of times we'll talk about the delta H as being the change in enthalpy. Remember, delta means change. The change in enthalpy. For reasons I'm not going to get into right now, and we'll come back to, we oftentimes put a little naught symbol, like naught as in, zero, a little naught symbol up here. That means that it's happening at standard conditions. I don't want to talk about that for right now. We'll come back to it. So that's what that means. All right. The equation definition so the word definition for change for enthalpy is a chemical potential energy that's expressed and observed when chemical reactions happen in terms of heat. All right. So if we put that in equation form, the delta H naught is going to be the heat of a reaction. Remember, Q is heat. So this is heat being evolved by a reaction. All right. And again, it can be positive or negative. And that's going to be divided by the number of moles. But this is actually a really particular number of moles and values. So remember back in first semester we used N when we were talking about gases. When we did PV equals nRT, the N was number of moles. Okay? So this is similar, but there's a wrinkle here, which is it's the number of moles of the limiting reactant. So whichever reactant runs out first, divided by its coefficient in a reaction equation, all right, in the balanced reaction equation. So this gets weird, and you don't need to worry so much about exactly why right now. It's going to make it easier for us to notate delta H later. But this is the way it works out. Some textbooks define this a little differently, and some are like really vague about it, and it drives me crazy. So this is the precise definition of N you need. If you don't do it this way, you get weirdo answers. So it's the number of moles of the limiting reactant divided by whatever the stoichiometric coefficient is in the reaction equation. All right, let's do an example and try to put all of that business together, okay? So consider the reaction, and it's provided here. It's HCl reacting with magnesium. You may remember this one from first semester lab. It makes a nice little bubbling reaction as the hydrogen gas is evolved. If 100 milliliters of HCl solution containing 0.1 moles of HCl, notice it's not 0.1 molar. I went ahead and did the calculation for you, and I'm telling you this solution contains 0.1 moles of HCl, and 0.050 moles of magnesium are combined in an open container. Now, it's usually kind of sort of closed. We usually use little caps to gently close these, but they're always open to the air, so that's what we mean by open. And the solution is found to raise in temperature from 20 to 30.5 degrees Celsius. Calculate the delta H for this reaction. Okay, so let's try to put our information together. So we got 100 milliliters of HCl solution. It's got 0.100 moles. We've got 0.050 moles of solid magnesium, and we're putting those together. All right, so the equation we're going to use here is delta H. Oh, and let's just do this. We've got a delta T here. Remember, delta T is T final minus T initial. The final is 30.5. The initial is 20.0. So that's going to be a delta T of 10.5 degrees Celsius. Okay? So the delta H is going to be the Q over N. So let's do the Q part first. So Q is equal to Cm delta T. That's the equation you'll recall that we learned in the previous lesson to calculate heat in a reaction. Okay? So we are going to now plug in, and this is into this equation. This is where folks get a little like confused, because it's like, well, what are we looking for the heat capacity of? And it turns out, remember that a aqueous solution is almost entirely water. It's like 99% water. Even a solution of, even though we name them like hydrochloric acid, the HCl that's in there is only in there in 1 or 2%, especially in the solutions that we tend to use in general chemistry. So we can just pretend, and it's going to be close enough for this, we can just pretend that 100 milliliters of water, or of HCl, is actually 100 milliliters of water, right? Because most of what's in the HCl solution is water. So that's all a long diatribe to say that we're going to take this 100 milliliters of hydrochloric acid solution, and we're going to say that's going to be close enough to 100.0 grams of water. Remember that water has a density of 1.0 grams per mils, so if you have 100 milliliters, it's like 100 grams. Okay? There are more precise ways to do this, but they almost always wash out when you go to the significant digits. So anyway, all right. So we're going to have 100 grams of water, because the HCl is dissolved in water. Oops, sorry, I'm skipping to the M. So the heat capacity is the heat capacity of water. We've got 100 grams of it. And we have a delta T of 10.5 degrees. And remember, that's positive, okay? So that's our Q. Now the Q is going to come out to be, 418 times 10.5 is. Rounding that to, what do we got? 3 significant digits. We've got 4,390 joules. Now remember, that's the Q for the water. We also learned yesterday that Q1 is equal to negative Q2. In other words, if this is the Q for the water, The Q for the reaction is the same value but opposite sign. So the Q for the reaction is 4390 joules. Okay, so be careful. You've got to remember this piece of information, that you calculated Q for the water, but the reaction that's taking place in the water is going to have the opposite sign. All right, so now, and that's why, and I didn't do it here, but if you'll notice on the previous slide, I called this Q reaction to kind of remind you of that. Okay, going back to here, delta H naught equals, so we got the Q, that's 4390 joules. What about the N value? All right, so we were told in the problem we have 0.1 moles of HCl and we have 0.05 moles of Mg. So the best way to do this is to take the moles of each thing you have and divide it by their stoichiometric coefficient, 2 and 1 in this case, and see which one is smaller. Whichever one's smaller, that's your limiting reactant, right? Because that's the one that would run out first because it's the fewest moles per however many moles are needed in the reaction. Anyway, blah, blah, blah. Take 0.1 and divide it by 2, and you would get 0.05. And you take 0.05 and divide by 1, you get 0.05. So either one, the N value is 0.05. So you don't have to worry about, well, which one is it? It doesn't matter. They're going to run out at the same time because they're both limiting essentially. So, all right. So we're going to use the smaller of those two values, which they turn out to be the same number, so it doesn't matter. And we're going to now plug those in, delta H. To the delta H equation, divide by 0.05, and that's going to come out to be negative 87,000. We've only got two significant digits here from the magnesium, right? So not 87, but 88,000. And the units would be joules per mole because we had joules in the numerator and moles in the denominator. So that's joules per mole. A lot of times for convenience, you'll see people express this as kilojoules per mole because for some reason thousands of joules seems, I don't know, inconvenient. So that's how we tend to express it. All right. So there's a lot going on here, right? So you got to do a calorimetry calculation first off. And you got to figure out what you're doing that for. It's the water the HCl is dissolved in. Use the heat capacity water. Use the volume of the solution. Change that to grams, which is 1 to 1. So that's easy. And then multiply by the delta T. Once you get the Q, remember to switch the sign. Okay. Plug that into your delta H equation. Calculate your N value. And that gives you the number. All right. Lots going on here. You need to practice this. So go ahead and pause the video at this point and work this problem on your own. If you get stuck after you start setting it up, hit play because I'm going to give a couple of hints. Okay, here are my hints. First off, you need a reaction equation, which I was mean and did not give you. So, but you should remember this. I hope, maybe from first semester, that HCl plus NaOH is going to yield water, because remember, Arrhenius acids and Arrhenius bases produce water plus NaCl aqueous. Okay, it's already balanced. Everything's 1 to 1 to 1, so that makes things a little easier, slightly. You have 50 milliliters of each of these. And they're both 2 molar. Now, notice that it's not that they contain 2 moles. They're both 2 molar. In other words, there's 2 moles per liter. You don't have a liter. And let's see, what was the... we can just go ahead and calculate. The delta T is 37.5 minus 24. So the delta T is 13.5. All right. Now... I was mean here, and I did not give you how many moles there are in each of these, right? I was, however, nice in that I set it up so that they're the same. So you need to bust out the molarity equation, which I know you haven't thought about in a while. So you need moles per liter. So you've got 2.0 molar equals moles over 0.050. Did I do that right? 3 times, yeah. Okay, and that's liters. So that means when we multiply it over... we've got 2 times 0.05. That's 0.1 moles. All right. You could have done this using the molarity as a conversion factor. That's also valid and probably easier, but this is the way that I think most of you tend to do this. Okay. Okay, so in other words, now you don't have to worry about this being 2 molar, right? You can say there's 0.1 moles of this guy. There's 0.1 moles of this guy. That's my hint. Okay, so hopefully that simplifies it a little bit, and you can finish it up from here. Okay, I really, really hope that you're actually doing what I'm asking you to do here and stopping and trying to do this on your own. You're going to learn it so much better if you try to do this, even if you can't finish it on your own, if you try to do it and then get stumped and then watch the solution. Okay, the solution, haha. Okay, anyway, bad chemistry puns. All right, so the equation that we're going to be relying on here is again going to be delta H equals Q over N. And so we're going to calculate our Q. And remember, that's the Q for the water that the HCl and NaOH are dissolved in. Sneaky thing here, they're both aqueous solutions, right? So there's, now we're making 2 assumptions now, which I know is too many for some folks to swallow, but it's close enough. So the 50 and 50 is going to usually make 100 milliliters. That's not technically true. It tends to be a little less or a little more when you combine them because of intermolecular forces and blah, blah, blah. But for the purposes of this class, we're going to pretend that volumes are additive and that you get 100 milliliters and that 100 milliliters contains 100 grams of water. All of those things are assumptions and they're not perfect, but they're going to be close enough. So we're going to do Q equals Cm delta T. The Q of the water is going to be 4.18 joules per gram degree Celsius. We've got 100 grams of water in our solution and we got 13.5. That's a 5 degrees. Oops. Degrees Celsius, run out of room there. Okay, so the Q for the water is going to be 4.18 times 100 times 13.5. By the way, I totally made these numbers up, so if you do this in the lab, you're probably going to get a really different answer. I mean, I think it's ballpark, but let's see, what do we got? 3 significant digits from the temperature, so that's 5,640. joules. Now that's the Q for the water. The Q for the reaction is going to be the negative of that. That's going to be negative 5640. All right. So the delta H, now plugging back in over here, I'm going to scoot my paper down a little bit. The delta H now is going to be negative 5640 joules over whatever my N value is. So going back up here, you have 0.1 moles of HCl, and that's a coefficient of 1. You have 0.1 moles of NaOH, that's a coefficient of 1. So 0.1 divided by 1 is 0.1. Both cases, they're both limiting. Honestly, unless you're observing a reaction in the wild, there's no reason to set these up in the lab and not have them both be limiting. It's not an unusual thing that they're going to both have the same N value when you calculate it. Anyway. So we're going to do the math, move the decimals. This one only has 2 because of the moles, 2 significant digits. Oops, I dropped my negative sign that I worked so hard to hold on to. Negative 56,000 joules per mole. And then, as always, if you prefer, you can express that as negative 56 kilojoules per mole. Either one's fine. All right. So lots going on there. You have to remember this business about the molarity from first semester to calculate the number of moles. And I know that's a pain, but it's okay. So it's good for you to have to remember these things. All right. Okay. So one more layer on top of the things we knew. We knew coming in today, we knew Q, we knew Q1 equals negative Q2. Now we're using all of that to do this business of calculating the delta H naught of a reaction from experimental conditions. Hope this was helpful. Leave me a comment, get in touch. Talk to you soon, and thanks for watching.